Hi class, welcome back to our lesson. Today we're going to be going through lesson 4, which is standard deviation. Your homework pages are as follows. Over here, they're going to be posted on Google Classroom as well. As we go through this lesson, we're going to be going through a few things. The first thing you'll know by the end of this lesson is the difference between symmetrical and skewed distributions. You'll be able to determine the different types of distributions by looking at their chart as well as what they mean. We're going to be talking about left versus right skewed graphs and distributions. You're going to find out how to find the standard deviation of certain data sets and as well as compare standard deviations to determine how close that data set might be or how far apart that data set might be. Okay, histograms can take on several common shapes. So when we're looking at our old our lesson 2, when we're talking about displaying data, you'll notice that histograms can look a certain way, but the ones that we've been graphing have kind of just been mostly symmetrical, right? So when we have two halves of an object mirror each other, is what we've been looking at. Everything's kind of going towards that central tendency. When we're talking about mean, median, mode, this is what we're talking about, that central tendency, right? You can also have skewed graphs. So sometimes you can have graphs that are leaning more left or leaning more right. So when something is a symmetrical distribution, it can be either normal distribution, which is what most of our stats tries to go towards, bimodal distribution, or uniform distribution. So the first example is of this normal distribution. So if we were to roll a pair of dice 75 times, the sum of each roll is recorded and graphed. So look at this. This is what it looks like. Sometimes you roll a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So that's just like how many times you're going to get these numbers when you roll a dice. So what we're graphing is the frequency. That means that this person got 7 16 times, 6 around 11 times, right? It just goes through it like that. What this is mostly referred to as bell curves, right? So you've probably heard like you got something and it's put on a curve, or a mound-shaped distribution. Even when we're doing grades, this is what I normally see when I do assessments in this class, and what we want to see. We want to see the majority of the people right here in the middle at about a level 3, right? The middle interval will always have the greatest frequency or the tallest bar. All the other intervals will either have decreasing frequencies as you move away from the center. So everything kind of peaks at the center, and as you move away from the center, it gets lower and lower. This might not be perfectly symmetrical, but it's still a definition of a normal distribution. As long as it's making somewhat of a curved or a bell curve shape, we consider it a normal distribution. Okay? And that is that. So I'm just going to highlight a couple of words here that we've used. So bell curve or round-shaped distributions, the middle frequency will always be the highest, right? As well as as you move away from the center of the graph, the frequencies will be lower. Okay. Another type of symmetrical distribution is actually this bimodal distribution, right? So we can say that we start off, decrease, and then go back up. So in this situation, the two extremes are actually the highest, right? So it kind of looks like an inverted normal distribution where the intervals with the highest frequency or the tallest bar are at either end of the graph, so the two extremes, and the interval with the lowest frequency is in the center. Frequencies can either increase or decrease as you move away from the center of the graph, right? So as you move away from the center of the graph, they're increasing. So here's the center, right? And then as you move away from here, they're increasing, and they decrease a little bit towards the end, but they're still increasing and decreasing. So this is like the class of 6 and grade 1 classroom. A class of grade 6 and grade 1 students was measured with their heights, and you recorded them on the graph. So that just means that we have short people, and then we have taller people, and the ones in the middle is kind of less, which makes sense because the difference between grade 6 and grade 1 kids, right? You're going to have two extremes, and then you're going to have some kids who kind of are in the middle there. Example 3 is what we call a uniform distribution. So this is if we rolled a die 50 times and then recorded its faces, and this is just one dice, right? You look at it and it's all kind of the same, because on a die there's more likely that you just have the same whatchamacallit, there's the same probability that you'll get the same die. Like the 6 faces have an equal chance of being landed on, right? So the intervals are approximately even. They're not always 100% even just because of probability and luck and chance. But if you were to roll a die, the chances you get a 1, the chances you get a 2, 3, 4, 5, and 6 are still 1 and 6. So they're still just equally as likely. Then we're going to move on to left skewed graphs, right? So left skewed graphs as well as right skewed graphs are graphs that are kind of moving and they're kind of favoriting one side. So you'll see like this is kind of favoriting the left side and it'll come down, right? They're not really in the middle. So even though there is one low frequency bar over here, right? It's kind of like it's leaning left, right? So that's what a left skewed distribution is. So if she picked a handful of quarters, recorded the year that each of them was made, she went in, found the frequency, noticed that more of the graphs were made closer to 2003, 1999, 1993 rather than earlier, but there's less made in 2008. So it's more skewed towards newer quarters. On the flip side, we can have right skewed graphs where the bar of the highest frequencies are on the left side and the frequencies decrease as you move right? So it's more shifted. It's kind of leaning left, right? So this is like a mound and it's kind of leaning left instead of leaning right instead of left. So that's just what it means. Left skewed and right skewed just means that one leans left, one leans right. Okay? So moving on, we're going to be talking about measure of spread, which is a way for us to talk about mean, median, mode and talk about data, but also consider that there might be a really large range. So calculating mean, median, and mode is a great way to find the center of your data. And this information is only really useful when the set of data that you're comparing is similar. So if you're looking at height and you have kids that are like the similar height, yeah, then having the mean, median, and mode makes sense. If you have, for example, a test, right, and everybody kind of scores decently on that test, mean, median, mode is a good measure of what your test was like. The problem arises is when you want to find out how far your data is spread out, right? You want to know, okay, if I have a mean of 75, that's fine, but from the lowest person in the class to the highest person of the class, what am I actually working with here, right? What does the lowest score, how does it relate to the middle score? And the middle score, how does that relate to the lowest score? So what I'm really trying to find out, is it more that score that was off to the edge is very like an outlier, or is it actually a more even distribution between each other, right? So I want to look at, is this more of a normal distribution? Is it skewed left? Is it skewed right? Is it uniform, right? I want to figure out what would my graph kind of look like. And you can actually do this by doing two things. You can find the range of your data set, and then you can find the standard deviation. So first, let's talk about range. The range of the set is a difference between the greatest and the least value of set data. So when you're comparing set data, you go and find the smallest number and the largest number, and you just compare them. When you have a small range, it just means the data is most consistent. So if you were in a class and you had students who scored somewhere between 50 to 80, right, versus a class that had someone who scored a 20 and someone who scored 100, the range is smaller on that first set of data, which means that that test was a little bit more evenly taken by the students, versus there was a large gap for the students in the second class. So we need to now consider, okay, what's going on? Why is there such a large gap in the understanding of what's going on in this test, right? So let's look at the following sets of data and figure out like why some of this information might be misleading, right? So here I am looking at this data, and I'm just going to go through and read it. I want to find the mean, right? I'm just going to go and do that in my head. I'm not going to write it out just because I don't have enough space on this graph. But when you're calculating the mean, what you're going to do is you're going to go ahead and just add all of your questions together, or all of your numbers together, and then just divide by how many there are. So if I'm going to go ahead and count this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 sets of data. I'm going to go ahead and just add everything together. So I'm going to do 0 plus 2 plus 2 plus 4 plus 4 plus 6 plus 6 plus 6. 8 plus 8 plus 8 plus 8. 10 plus 10 plus 10. 12 plus 12. 14 plus 14. 6 plus 16. Added all of those together, and then I divided that by 20, and I got 8. Now, I know there's 20 sets of data here, or 20 points here, so I'm just going to go 1, 2, I'm going to find the middle, which is going to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I have to do the same thing on the other side, going backwards. I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So my median here is going to be, it shouldn't be, there's an even set, so it shouldn't be like that. So this is going to be the 10th one, right? Since they're both the same number, we can just say the median is 8, because when you take those two numbers and you add them together and divide them by 2, it's just going to be 8. So our median is 8. Right? Let's find the mean median here as well. So I'm going to do, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 points here, right? Median is easy to find. Just find the number that's in the middle, which is going to be 7. 1, 2, 3, 4, 5, 6, 7. So the median here is 8. If I want to find the mean, I'm just going to add everything together, divided by 15, which is also going to give me 8. Notice how these two sets of data are actually pretty different, but they had the same median and the same mode. Right? This information can be misleading. And the reason that this information can be misleading is because if you look at the data and if you look at the graph, look at this. This is a normal distribution, right? We peak kind of at 8. Whereas this one is more even. And even if you look at the numbers, you'll notice that you go up, you have more 8s, then you go down again, right? So this information is misleading because one graph is actually bell-shaped and the other one is uniform. But when we look at the calculations made on mean, median, and mode, what happens is that they actually have the same median and they have the same mean. So if I was looking at this without looking at a graph, I could just say, okay, yeah, they're the same type of distribution, but they're actually not, right? What they actually are is one is shaped normally, it's a bell shape, and the other one is uniform. A way that we can figure out and compare these graphs, right? I'm just going to write this down, sorry. Because one graph is bell-shaped, right? So set A is bell-shaped. Other is uniform. But the calculations make them appear that they are the same. Even though they're spread out quite differently. So something that we can do to further compare these graphs is actually compare their range, right? So let's compare their range. So when I'm going to measure the ranges, I'm going to do, for set A, I'll do it in pink. Okay, so we'll make set A pink, and then we'll make set B blue. Green. Right, so let's do set A. The lowest number on set, or the highest number on set A is 16. Right, so I'm going to go say 16. And the lowest number is 0. Right, so my range here is 16. That means that there's 16 points that can happen in between here, right? On the other hand, for set B, I have, the highest number I have here is, I believe, 12. And the lowest I have is 4. Equals 8. And so the range on set B is 8. And if you think about it, right, the way that the intervals work is that on set A, I will have significantly more intervals. So I'm going to have to spread out, right, my numbers over a larger area. Whereas with set B, there's less intervals, there's less. So the amount of data I have is significantly closer to each other, right? So that's just what you need to consider. When you have a smaller range, you have less data to work with. So it means that they're more uniform in their distribution. Okay? So another example is that say we have these twins, Toby and Moby, right? They work at this local pizza shop. Their manager is deciding whether or not to give them a raise. When she looks at their data, this is what she sees. Which one of these deserves a raise? So let's go look at this data. The first thing you're naturally going to do is be like, okay, whoever makes on average more pizza per shift, right, should deserve the raise. Let's go find who makes the most pizza per shift. So let's do Toby first. So I'm going to do Toby in this blue color, right? And we'll do Moby in pink, right? So let's do Toby's number of pizzas. So Toby, to find his mean, we're going to just do 54 plus 152 plus 180 plus 12 plus 72 plus 126, which is adding up all of his pizzas, plus 104 plus 132, right? And I'm going to take all of them. She's measuring them over 1, 2, 3, 4, 5, 6, 7, 8 shifts, right? So divide everything by 8. So I went ahead and added everything at the top, and I got 832. Divide that by 8 is going to give us 104. That means on average per shift, Toby makes about 104 of those pizzas, right? Let's go ahead and find how much Moby makes. So Moby, we're going to do the same thing, right? We're going to go adding 132 plus 104 plus 102 plus 120 plus 86 plus 1 day he made 12 plus 96. Right? Take all of them, divide it by 8. 832.8. Right? This is also 104. So if you're looking at just the averages, it looks like Toby and Moby are equally as deserving of the raise, right? So let's go look at the range of these two data. So the most pizzas that Toby makes is 180, right? 180 minus the least amount he makes, I think, is 12. So the range is 168. Over here, the most number of pizzas that Moby makes is 180, and the least he makes is 12 again. So the range here is also 168. So now, according to their mean and according to the range of pizzas they make, they kind of have the same range and the same mean, right? So at these statistical levels, both these employees are pretty equal, right? But if you go back and you look up at Moby's data, it just looks more consistent. He's consistently making the same number of pizzas, right? What she needs to do is she needs proof to support her claim. You want the more consistent employee. You want somebody who is consistently doing the same. Like Toby is like, yeah, like some days I'll make like 12 pizzas, but other days I'll make 180, right? But then I'll go back to making 54, but then I'll go and make 72. Then I'll make 126. That's not somebody you want working for you, right? You want someone who's consistently showing the same level of work. So you want more of a uniform distribution, less of a skewed distribution or even a normal distribution, right? How you can do this is you can actually see how uniform a distribution is by looking at the standard deviation, right? So if you look at the standard deviation, what the standard deviation is actually going to tell you is the average distance of a set of values from the mean. So it tells you, okay, if this is your central average, how far, right, are all of the values from that standard middle section? Like how far is the range between the two? How far do they consistently stray from the norm, right? So when we calculate standard deviation, this is our sigma is what we use. We use the term sigma, right? Sigma is equal to x1, which is whatever your x value 1 is, minus the mean squared, plus x2 minus the mean squared, x3 minus the mean squared, so on and so forth for however many sets of data you have. X1, X2, X3 are values in your data set, right? So those are the numbers. Those are his number of pizzas that he makes, right? That's what we're looking at. We want to know how many pizzas he makes, so we're looking at his number of pizzas, right? So in order for us to calculate sigma, what we actually need to do is we need to figure out the difference of each value from the mean, right? Then we need to square each difference, then add up all your answers at the bottom, and then divide them by the sum by the numbers of numbers in the square root. And divide by the number of numbers. So like you go back and you divide by however many terms you had, and then take the square root. And I know this seems really confusing, so I'm going to walk you through this. The first thing we need to figure out is the mean, and we already figured that out. For both of them, the average here is 104, right? But let's do Toby's set of data first. So I just went and I took Toby's, I like to make this graph, this table like this. So I say, okay, this is the number of pizzas he made. I want to find out what the number of pizzas is minus the mean, and then I take that number and I square it. So I actually instead of putting it all into this one super long equation, I actually just go and do everything in a table form because it's just easier to be able to measure it like this. So let's do that. I know the mean is, and we're going to do this in blue because this is Toby. So 54 minus 104, right? 54 is the number of pizzas. I just got that from here. 104 is the mean, which is just always going to be the same. So I know that's negative 50. Then I'm going to just go over and do my next column. I'm going to do negative 50 squared is equal to 2,500. Right? And I'm going to do that for every set of data that follows. So I'm going to do that with 152 minus 104 is going to equal 48. Then I'm going to take 48 and square it. Right? Then we get 2304. 180 minus 104 is going to give me 76. I'm just going to continue to do this. 76 squared is equal to 5776, right? Then I'm going to take 12 minus 104, and make sure that you always put your numbers in brackets, otherwise you're going to get negatives. And you shouldn't have any negatives over here, right? So it's going to be 180, 84, 64, right? Then I did 72 minus 104. That gave me negative 32. Then I did negative 32, and I squared it. And I'm just throwing these into my calculator, right? Then I did 126 minus 104. And then I did, okay, that gives me 22, right? Then I did 22 squared, and that gave me 484. 104 minus 104 is just 0. 0 squared is equal to 0, right? Then I have 132 minus 104 equals 28, right? And that is 28 squared, which is 784. So it would be 21336. So how I got that number, I'll just show you how I got this number before I do it. I went and I added all of these together. So I went and added all the difference from the mean squared, and then I added all those numbers together. So I did 2,500 plus 2,304, 57 plus 6, and then I added all those together. And my final answer here was 21336. So do you see this like portion where it says you have to add all of them together, right? I just did the numerator all as a step in my chart, right? So now I can take that numerator, so sigma is equal to square root of the total, which I had from the first one, right, divided by n. And n is just the number of numbers there were, so it's 1, 2, 3, 4, 5, 6, 7, 8. That's how many pizzas he made, right? So I'm just going to do that, and I'm going to say, okay, so I have, and I'm going to do it in blue again, just because this is just for Toby. So that was a total. Then I did divide it by the number of pizzas, which was 8. And then I square rooted. right? So then when I did that, 54, 64, right? When I did all the math, that means that the standard deviation here is 51.64, right? Not 54, it's 51.64. That's fine, but that's meaningless to us, right? In order for standard deviation to mean something to us, we actually need to compare it to another set of data. So we know that Toby's standard deviation is 51.64, but in order for that to actually mean something to us, we need to compare it to the standard deviation for Moby, right? So let's go ahead and compare it. I actually went in and I wrote in whatever your calculations were going to be, so we just need to fill them out. So I did 132 minus 104, which is again the mean for Moby, right? Which is going to be 28. And then 104 is 0, negative 2, 16, negative 18, negative 92, 76, and negative 8, right? So then I'm just going to go take 28, square it, and that's going to give me 784. Then I'm going to take 0 squared is just 0. Negative 2 squared is just 4. 16 squared is just going to be 256. And then 92 squared is 8,464. 76 squared is 5776. And then 8 squared is just 64. So I went ahead and added all of these together, right? So I did 784 plus 0 plus 4 plus 256 plus 324 plus 8,464 plus 5,776 plus 64, and I got 15,672, right? So now I'm just going to go find my sigma value. I'm going to do it in pink. So my sigma value is just the total divided by n, and they were always over 8 shifts. So let's go ahead and do 15,672 divided by 8. And I ended up getting square root of 1905.9. And my sigma ended up being 44.26. So now this is significant. Notice how your standard deviation is lower here than it was here. Here it was 51. Here is 44.26. What this basically means is because Moby's standard deviation is smaller, right? It means that Moby's data is closer to the mean than Toby's. So Moby is more consistent and deserves a raise. When you're looking at standard deviation, the closer the data points are to the mean, so the closer the data points are to the mean, the standard deviation is closer to 0. So with that being said, if the data points are further away from the mean, which means that they're more distributed away from the center of that graph, right, then that standard deviation is far from 0. It's more 52, 56, 100. 100 would be a lot further away from the mean, right? If the data values are equal, right, so they're all kind of consistent and uniform, the standard deviation is 0, which makes sense because that means that they all are the same, right? There's no big difference between them. When you're comparing data sets, the smaller the standard deviation, the more consistent that data is. So even here, notice how Moby's standard deviation is smaller than Toby's. That means that while they have the same average, they have the same median, they have the same range. So on paper, they all look like they're doing the same level of work, right? The standard deviation helps us realize that Moby is actually way more consistent than Toby is, right? And that is why stats is important, and which is why we study, especially standard deviation, is because sometimes when we're looking at numbers, they all look like they're saying the same thing, when the reality of the situation is that sometimes just by looking at the standard deviation, which is why standard deviation is such a big thing to know in stats, just by looking at the standard deviation, you can tell right off the bat that they aren't actually the same. And even though their mean, median, and their range say they are, they're not. Because if their standard deviation is closer to 0 or is 0, it means the distribution is more uniform, which paints a completely different picture than something that is normal or mound shaped. Okay? So that's why standard deviation is really important. And in order to really understand the significance of standard deviation, you do need to calculate both of them. Okay? And that's it. That's it for standard deviation and normal distributions.